Here we are. This is the end of the semester, chapter number 10, properties of gases. We've already talked about gases a little bit when we talked about different states of matter, but things that you need to know about gases are their fundamental properties, one of which is that they have an indefinite volume. So what that means is if there is a small amount of gas, what that's going to do is it's going to expand to fill whatever container that it's in. So it's not limited except by the container that it's in. So it has an indefinite volume. It also will fit that shape of that container. So it has an indefinite shape. Gases are compressible. And finally, all gaseous mixtures are homogeneous. So you have an even distribution of the different molecules or atoms that make up a gas. In the air around you, molecules only take up 0.1% of the space. The rest of it is just empty space. So the space between those different molecules and atoms of a gas, well, that's just empty space. Now, gases versus vapors. So when you think about a vapor, what I want you to think is that a vapor is the gaseous state of a substance which is a liquid or a solid under ordinary conditions. So gasoline, for instance, or a diesel fuel produces vapors, and those are the gaseous state of a substance in which a liquid or solid under ordinary conditions. Okay. Now, measurable properties of gases. You can measure the temperature of a gas. You can measure the volume of a gas, the amount, the pressure, and whenever it comes to pressure, you should be thinking about the force per unit area of that gas. The common units for pressure are going to be, this is mmHg, or millimeters of mercury, or atmospheres. So 1 atmosphere is equal to 760 millimeters mercury. Now that millimeters mercury, that does have a specific instrument associated with it. Where that number comes from, it is derived from an instrument that we're going to talk about in just a moment. Older unit, and not quite used as frequently, but you can see it from time to time, and that is a torr. Comes from the name of an Italian scientist, Torricelli. It's somewhat outdated, it's not too commonly used, but effectively 1 millimeter mercury is equal to 1 torr. So what that means is 760 torr is equal to 1 atmosphere, just as 1 millimeter, or 760 millimeters mercury is equal to 1 atmosphere. So that's a kind of outdated term, but nevertheless, it's good to have in your back pocket in case you ever need it. Remember, mm is millimeters. So measuring pressure can be done using a couple of different instruments. One instrument known as a barometer, and you might be familiar with that from like barometric pressure or something. So if you look at atmospheric pressure, is also known as barometric pressure. And this is used to measure the pressure of an unenclosed gas. Okay, a manometer, on the other hand, that is an instrument used to measure the pressure of an enclosed gas. And we're going to look at a pair of each of these on the next few slides. So a barometer, well, is dependent on a pool down here. So we've got a pool of a solution. Now that solution is mercury. So what you can do is use this tube right here. It is closed on this end, opened on this end. Fill this with mercury and flip it so that the closed end is exposed, the open end is in that solution. And what is going to happen is, based on the barometric pressure, based on the atmospheric pressure exerted on this pool or relieved from this pool, the volume or the height of that mercury in this chamber is either going to go down or it's going to go up. If it goes up, what does that mean? That means that the pressure, or there is pressure being exerted on this body right here, forcing that solution up. Okay, now this is our unenclosed gas. So basically, whatever gas is out here that is pressing down on that or not pressing down on it is going to cause the mercury in this chamber to fluctuate, either going down or going up based on the pressure of that gas. Now, a manometer is an instrument used to measure the pressure of an enclosed gas. So our enclosed gas is found in this round bottom flask, or this round bottom piece of glassware. Now, let's say that we had a reaction that produced some gas. We don't know what the pressure is of that gas. And as we'll see later on, if you know the pressure of it, then you can learn some other information, for instance, the amount of that given gas in there. Now, in order to start this out, you have this chamber, this kind of snake-like chamber that has some curves to it, and you're going to fill that with mercury. And when you fill that with mercury, what you can do is you can hook this piece of glassware up to it, this round bottom flask, open this valve, and what's going to happen to the gas that's in this, that I just scribbled with red and now I'm scribbling with orange? What's going to happen? Well, that gas is going to fill this chamber. And whenever it gets to this mercury, what's it going to do? It's not going to react with that mercury, but instead it's going to press that mercury downward. And if it presses that mercury downward, what does that tell you? That tells you a little bit about the pressure of gas in that piece of glassware right here compared to the pressure outside of it. I always kind of think about it like a seesaw or a teeter-totter whenever you're a kid. Whenever you start out using that seesaw, well, you've got this central axis, this fulcrum in the middle. Now, if you put a heavy weight on this end compared to a light weight on this end, what's going to happen? Well, it's going to push downward. So now you've got it looking like this. So you've got that light weight way up in the sky and this heavier weight right there. So similarly, if you have a pressure or a gas in this chamber that pushes this mercury down, what does that tell you about the atmospheric pressure? It tells you that there is a higher pressure in this chamber than outside of that chamber. Because remember, this tubing is open on this end and, well, it was originally open on that end, but you hooked it up to your chamber and you allowed that gas to fill it. You've got basically competing forces there. Okay, so you can use that information to compare the pressure of the gas and the atmospheric pressure. So you could look at the pressure of the gas is equal to your pressure of your atmosphere versus the change in that delta H, or a change in H, the height of that gas. So if you look at it from here was our starting point and it went up to here, let's call that 5 millimeters mercury. Well, then if you know the atmospheric pressure is 760, well, then the pressure of that gas is 760 plus 5, so 765. Another way to look at a manometer is by seeing, well, if the gas is less, then you might have something where the pressure of the gas is lower than the atmospheric pressure, which means that the mercury level is going to go toward your chamber. Okay, so I think the best way to do this, the best way to address this is by looking at some practice problems. So there will be some practice problems on your Canvas page, or there are example problems on the homework. Take a look at those. Ultimately, this is just movement of that mercury. Is it going up or is it going down and everything like that? All right, well, I hope this is helpful, and we'll continue on in just a moment.